we'll be looking at reactions that involve a different type of reaction intermediate. All right? So far, all of the reactions that you've looked at, whether they are substitution reactions or elimination reactions or electrophilic addition reactions, all of those involved ions. Nucleophiles are usually anions reacting with cations. There were some ions somewhere in the reactions. So now we're going to look at reactions of radical species. Okay, radicals are species that have an unpaired electron. Okay? Before, we always worked in pairs of electrons. We used arrows to show the movement of pairs of electrons. Now we're going to have to do them one at a time. I'll just write this in here now since I left a spot out before. There are really two ways to break bonds. And up to now, the type of bond breaking that we've seen was always splitting a bond with a pair of electrons going to one side, right? And they could go to either side. I'll just show them going to Y right here. That would leave an X plus a Y and a pair of electrons over here. So that bonding pair ended up on one atom, right? And so this Y would have a minus charge on it now. The X would have a plus. This is called a heterolytic bond cleavage. I'm going to run out of space anyway here. This is heterolytic. Hetero means that it's being split unequally. Lytic means to lyse, like you maybe learned in biology, means to break or to cut. So in radical chemistry, we're going to take something like this, X and Y, but we're going to break that bond having one electron go to each side. And so to show the movement of single electrons, we're going to show these type of arrows that only have one side of the arrow on them. And so we're going to have one go to that side, one go to the other side. And if we do that, we're going to get X as a radical and Y as a radical. All right? This is termed a homolytic bond cleavage because it's very equal and very equitable. All atoms are happy. They all get an equal share. Okay? So this is what we're going to look at more in this chapter. All right, so here's the learning objectives for this chapter. So we just already learned, look at, we're way ahead of ourselves. We already learned about homolytic and heterolytic bond cleavages. All right, we're going to look at relative stabilities of radicals, and we're going to focus first on the addition of halogens, particularly chlorine and bromine, to alkanes. Okay, we're going to learn how to predict the products of those reactions, and we're going to learn how to draw out their reaction mechanisms. Okay? So let's just think back as far as we're going to do a reaction of an alkane here. Have you ever learned any other reactions of alkanes? Did you? Yeah. Have you ever learned? Have you learned halogenation yet? Yeah. Well, what's another reaction of an alkane? I got the halogenation down there already. Let's think of something else. You probably performed one of these reactions already today. No, not a substitution. Did you? Maybe you guys did halogenations in their lab today, and I don't know. What's the main thing that we use alkanes for? Huh? Combustion, good, right? They're mostly fuel sources. I know I used methane this morning to heat up my house, and then I used gasoline to burn to drive my car into work, right? And so the main reaction that we know of alkanes is combustion, right? So if we just write out the most simple reaction here, so starting with methane. So methane is just natural gas. So this is what I used to heat my house this morning. We react that with oxygen. And what do we get from combustion? All right, CO2, good, plus water. Okay, so if we balance this, we end up using 2 oxygens, and we get 2 waters, and we also get a lot of heat. Okay? So this is just a common reaction. However, it doesn't have much use for us synthetically, right? Unless we want to convert alkanes to carbon dioxide. So what we're going to do is learn new ways that we could utilize alkanes as a starting material. Okay? So for halogenation reactions, if we just react chlorine with ethane, nothing happens. Okay? So we have to do something to help kind of kickstart this reaction. And so what it usually is that we have to add H nu, some light to this, or we have to heat it up. Okay, so we have to trigger the reaction somehow. And if we can do that, then we can add a chlorine to this, and we're replacing a hydrogen, so we get an equivalent of hydrochloric acid. And like you guys mentioned, this would be a substitution reaction. Okay? So we're kind of using what we would consider as a very unactivated molecule, right? It's not acidic. There's, usually we do reactions on molecules that have functional groups that have some reactivity, but an alkane is pretty unreactive. And so we're taking something unreactive and we're actually making it into something more reactive. All right, so let's radicals a little bit more. We already said that radicals have an unpaired electron. What about the structure of radicals? Okay, so radicals, we can think of them as kind of being in between. If we had 3 possibilities, I'm just going to use this Z here. We could have a Z with a plus, we could have a Z with a radical, or we could have a Z with 2 electrons and a minus. Okay, so we're kind of right in the middle. We've learned about carbocations and probably carbanions, but radicals are right in the middle. All right, we know that carbocations, what's the geometry in the hybridization of a carbocation? So R plus, what's the hybridization? sp2, right? It's sp2, and so it's trigonal planar. What about an anion, a carbanion? sp3, because now we have a whole pair of electrons that have to take up some space to make a tetrahedral. So this is sp3. So again, the radical is right in between those two, so it's not really clear, I think, which way it would go. But basically what we're always told here is that radicals behave, in this sense, a little bit more like carbocations. All right, so they are sp2 hybridized, meaning that they're going to be trigonal planar. So the drawing there is supposed to show it has the bonds in the plane here. Here's the dashed one back behind. So those are planar, and we have a p orbital, and the radical, the lone electron, is in that p orbital. All right? All radical reactions have 3 general stages. Okay, the first stage is called the initiation. And this is where we essentially take non-radicals and we generate radicals. Okay? The second stage is called a propagation. And in this part, and it can involve more than one step, it usually does, what we're going to do is take a radical plus a non-radical, and we're going to make essentially a new radical plus a new non-radical. Okay, and because one of our products is a radical, it can go back and react again, and so the propagation part of the reaction is really like a chain reaction. It's a cyclic process, right? So after 2 steps, we make a product, and that can go back at the beginning and react again, and it just goes around and around in a circle. Okay, so this is where most of the product is formed, is in the propagation steps. The third stage is called termination. And this is where 2 radicals come together and form a non-radical. And if that happens very much, then there's no radicals anymore, and the reaction stops. Okay? So this is a radical plus another radical. So this is really just the reverse of what I showed you as the homolytic bond cleavage. It would be 2 electrons coming together to form a bond, to form a non-radical. Right? So this is a process that essentially kills the reaction. Okay? So every radical reaction process will involve these 3 parts. All right? Okay, so let's start out by looking at the bromination of ethane. Okay, so we'll start simple here, and we don't have to draw a lot of atoms to do this. Okay, so what's the first stage? Initiation, right? So we can't do a radical reaction unless we generate radicals. So the way that the initiation goes is that it involves bromine, and we either heat or shine light on bromine, and because the bromine-bromine bond is reasonably weak, we get a homolytic bond cleavage of the bromine-bromine bond. Okay, so one electron goes to one bromine, the other electron goes to the other bromine. And we just get 2 bromine radicals. Okay, so that's the initiation. What's step 2? Is the propagation. All right, so we're going to take a non-radical. So this is going to be our starting material. Okay, and I'm going to single out one hydrogen up like this so we can do the reaction with it. And that's going to react with a radical. So that's going to be a bromine radical. Okay, the bromine radical is essentially going to abstract or pull a hydrogen atom off of ethane. Okay, so this, we're going to show it like this. This electron is, we're going to show kind of this bond to nowhere. And that's going to combine with an electron from the carbon-hydrogen bond, and the other electron in that carbon-hydrogen bond is going to go over onto the carbon. And if we do that, we get this ethane radical plus, what else do we get? Yep, HBr. Okay, so we're not to our product yet. So we could, you know, an easy, and it always looks like a good shortcut to do here, you just go, aha, look, I have a bromine radical, I have an ethyl radical, I could just combine those and get our product. But that's a termination step. So if you do that right away, it just kills a reaction. So that's not how most of the product is formed. All right? The way that most of this product is formed is the reaction, again, another propagation step. We're going to react the ethane radical with Br2. Okay, so again, propagation is usually a radical and a non-radical. So this radical combines with a bromine, splits that bromine bond, we end up with, draw it down here, product plus, what else do we get? A bromine radical. Okay, and look, this bromine radical here can then go back up and do the reaction again. Yeah, question?
Could two carbon radicals connect to each other and then form a 4-carbon?
Okay, good question. So the question is, could two of these ethane radicals combine? And that can happen, and we'll talk about that in a second, because that would be part of a termination step. Okay? So what happens here is usually we have at any time we have a very small number of radicals. Okay? We don't shine enough light or heat to make a ton of radicals all at once. We have a small amount of radicals, and it just cycles around this process right here in this chain reaction. Okay? And as our starting material starts to go away, then basically the radicals start to find each other, and then the reaction starts to terminate. All right, so here's our product. Let's just identify. This is where most all of the product is going to be formed. Okay, but the last step is the termination. And the termination can be the combination of any two radicals in this process. Okay, so it could be like what was just suggested. One possible termination would be two ethane radicals come together. All right, so these could combine, and it would form just butane. Okay. What are some other termination steps we could show? Yeah, two bromine radicals could come together. And this would essentially go back, and well, this wouldn't be so bad, but, well, it would kill radicals, but it would form bromine, which is just a component of the reaction anyway. So it's not really giving us a side product, at least. And what else?
Just a question.
Yeah.
If you were still applying the heat or light, wouldn't the bromine radical just form again?
Right, good question. So the question was, if we were just continuously doing light, wouldn't that bromine just homolytically cleave again? And that could be possible. I think sometimes you only have to kind of blast it with light at the beginning and then let it go. But I remember there's some of these kind of reactions. We used to do this lab experiment for the organic chem lab when I was teaching in Hawaii, and it was a bromination reaction. And it wouldn't work very well in the lab, but then we'd take these test tubes and we'd walk them up to the roof out in the sun, and all of a sudden they'd have this sun hitting them and the reactions would start because it was a radical mechanism. Okay, so there's one more termination that we could do. Right, we could have a bromine radical plus the ethane radical, oops, which would essentially just give us some product as well, right? That's what we talked about up above. I guess I'm going to draw it on this side. Okay, so we're always going to split it up into these three stages. All right, so for example, if I asked you to write out a radical reaction mechanism on perhaps an upcoming exam, you might want to make sure you list all of the reactions and show each of those steps, right? Show all the possible termination processes and things like this, okay? At least that's what I would suggest. All right, any questions? Yeah?
So these are all probabilities, but will all of these happen?
So the question is, will all of these happen? Certainly the initiation and propagation will happen. The termination steps, I would think, would not necessarily be equally, probable. The energies of each of those are going to be a little different.
So some are favored over others?
Probably. I don't know exactly which ones or something. We could probably figure that out by calculating the delta H's and stuff like that, but I don't like to do those kind of calculations. Good question. Yeah?
So, could the ethane also form, like, could that be an initiation step as well?
Oh, okay. So could the ethane molecule itself homolytic cleave? I think that that's very unlikely because that carbon-carbon bond is way stronger than the bromine-bromine bond, okay? So that's very unlikely to happen, okay? We only see cleavage, we saw some cleavage like that, kind of like that in mass spectrometry, but that's a much higher energy process. Yeah.
Bromobutanes from the termination.
Oh, okay. So I guess the question partly is just, what about those termination products and how many or how much of those would be around, and are they going to actually contribute to some, significant portion of product, right? And if they did, then if the butane was formed, are you going to get products from that as well? I think the answer there is that if we run the reaction under conditions where the concentration of radicals is low, and we never have very many radicals, then we're never going to form very many termination products. Okay, so we run it under those conditions, and so the concentrations of those byproducts is very low to insignificant. Okay, good question. All right, so let's look at what happens if we chlorinate now a molecule that has more than one type of position. Okay, so we've got propane now. Propane has methyl groups and a methylene in the middle. So we have two possible products, right? We could have a product where the chlorine went to the center position, or we could replace one of the methyl hydrogens. Okay? So let's just think about the probability of each of these products being formed. And if the probability of the products being formed is related to how many of the hydrogens that are available, then we know over here we essentially have two methyl groups, right? That equals 6 hydrogens. We have one CH2 group in the middle. That gives us 2 hydrogens. So if the outcome was purely statistical, then we would expect a 1 to 3 ratio. Okay, if all reactivity was the same. So, have you seen anything in organic chemistry so far that would lead you to expect that kind of outcome? Usually there's some differences in energy, right? So, actually what's observed is that we get about a 1 to 1 ratio of these products. Okay, so what does that tell us? Yeah.
The greater substitution stabilizes the radical?
Right, so I think that's where we're leading. So maybe what it suggests first is that for some reason the more substituted position is more reactive, right? Because we're seeing more product there than we expected. So for some reason, the secondary position is favored to some extent. Not a huge extent here, but it is, kind of leaning it back towards that side. All right, so the question would be why, and if we think back to reactions that involve carbocations, we usually looked at the stability of the intermediate, right? So maybe this would suggest that we have that the secondary one would have a more stable radical intermediate. Okay, maybe. All right, so question.
So the observed ratio is a 1-to-1. So they were, even though we expected it to be different than that,
Right.
They ended up being equal. So
Right.
Can we really say that they were favored, or is there something else going on?
Well, because if it was just statistical, then we'd have 1 to 3, right? So now, even though there's less hydrogens at the CH2 group, we're getting equal products. So that per hydrogen, that secondary position is reacting more. Okay? So it's not dominating it or anything, but it's kind of compensating at least.
But it's a general principle would be just like stabilizing carbocations or stabilizing radicals.
Right, that's where we're going. Yep, yeah. Well, let's look at all of the reactive intermediates, and we'll add radicals to those. All right? So we already know something about... Yeah. Oh, sorry. Yeah.
So if we were asked to do, like, the mechanism we did for bromination, for chlorination, would we have to do both products? Like, both the initiation?
Yeah, so if I ask you to do a mechanism, usually what I would do is I would say go from this reactant to this product. Okay, so I'd probably ask you only to show one product. Okay, if you were, it would only be one more step in the mechanism if we wanted to show both. But I'd probably ask you to go to one. Yeah, I'll try to be as clear as possible about that kind of question. Okay, so if we look at these different carbocations, right, this one has all R groups, so this is a tertiary carbocation, this would be secondary, this would be primary, and then methyl. All right, so which of those is most stable? The tertiary, right? So stability goes this direction. Okay? Because those alkyl groups can donate some electron density to the carbocation. So what about carbanions? If you can see the little minus charges in there. It goes in the opposite direction, right? Because cations you want to stabilize by donating electrons to them. Anions, if you donate electrons to an anion, it just builds up more charge and it makes it even less stable. So you want to pull electron density away from an anion, right? And so by having alkyl groups donating, it makes it less stable. So the stability of carbanions goes in the opposite direction. Okay? So radicals, we can think about radicals is that they're not charged, but they're still short of an electron, right? They don't have a complete octet. Those carbons only have 7 electrons around them. So they still want more electron density. So their stability mirrors that of the carbocations. However, what I would say is that the energy differences between tertiary and secondary or secondary and primary is not as great. Okay? So we follow the same as carbocations, but the delta E between these is less than for carbocations. Yeah.
So is shining a light like the only way to create a radical, or what are some of the other?
No, you can use heat as well. Those are usually the two main ways. Yeah.
Would different kinds of radicals be affected by hydride and methyl shifts to try to save them?
Oh, okay. So the question was, with carbocations, we saw that if we have a more highly substituted position next to the carbocation, that we could get either hydride or 1,2 alkyl shifts to generate a more stable carbocation. Those kind of shifts do not take place for radicals. All right, bromination reaction of propane as well. All right, so in this case, still our expected, if we just went based upon statistics, would still be 1 to 3, right? It's basically the same reaction, we just got a different halogen. But the observed is now 99 to 1. All right? So for bromination, the more substituted position is very much preferred. So this is a very selective reaction. Okay? What kind of selectivity do we have going on here? What do we call it? It's regioselectivity, right? This is regioselective. Okay, so why? Why is bromination so much more regioselective than chlorination? All right, so we can action energy diagrams. Okay, so the rate determining step in both of these reactions is the abstraction of the hydrogen atom off of the reactant. So here we have X radical in one of the reactions, it's chlorine, in the other is bromine, right? And so this is the rate determining step is those two coming together. Oops, ended up with to form our carbon radical plus HX. Okay, and this could be either on the end or it could be in the middle, right? But it's the step of pulling off the hydrogen that's the rate determining step. Okay, so what I've done is I've lined up the two reactions. So over here we have chlorine, and over here we have bromine. And they're both leading to the formation of the two radicals. Okay, so here's the primary radical, and here's the secondary. And so I just lined them up so that matches the energy of the secondary over here, and it matches primary over here. Okay? So the interesting thing about this is that it's not only the organic part which influences the relative energies, okay? It also depends upon the halogen radicals and, you know, the products that are formed. So notice that in the chlorination reaction, this rate-determining step is exothermic. Okay? Starting at a higher energy and it's going to a lower energy. Right? In the bromination step, it is an endothermic step. Okay, we're going from a lower energy to a higher energy. So now, if we think about which of these products is forming faster, it's not really the intermediate that controls the rate of the reaction, right? What is it that controls the rate of the reaction? It's the transition state, right? Or the activation energy. And you learned last semester something called the Hammond postulate. And this is what we could use to relate the relative stabilities of carbocations to the relative stabilities of the transition states leading to those carbocations. And what the Hammond postulate says is that the transition state will look most like the species to which it's closest in energy. So in the exothermic reaction with chlorine, the transition state is going to look more like the reactant. But both of these reactions start with the same reactant. And so there's a very small energy difference in the transition states for the chlorination reaction. Whereas for the bromination reaction, the transition states are going to look like the products because it's an endothermic step. This is like the carbocation reaction. And because we have a bigger gap in the difference in energies between the two radicals, we have a bigger gap between the energies of the transition states. Okay, so this has a larger delta E, the difference in energy between the transition states. And it's the difference in the transition state energies that controls the ratio of the products. Okay? Most of the reaction, almost all of the reaction, follows right over the small energy barrier. Okay? So this is why this is so much more selective. Okay? Okay, so because of this increased selectivity for bromination, the bromination reaction is much more useful in synthesis than the chlorination. Because the chlorination, if we have different, types of carbons, different substitution patterns, chlorination will give a big mixture of products. Okay, but the bromination is very selective for the most highly substituted position. Right? So if we do a bromination reaction of this ethyl cyclohexane, where's the bromine going to go? To the tertiary position. Right? And it's going to be very selective to that position. All right? What about this bottom molecule? Where's the bromine going to go? Tertiary one, so it's going to go over here, right? Why doesn't it go over here? That looks like the most highly substituted position. Yeah, there's no hydrogen there, right? So we can't abstract a hydrogen and generate a radical. Okay? All right, so let's just finish off by thinking about how we might be able to use halogenation reactions in synthesis. Okay, so now, instead of starting with an alkene or an alkyl halide or something like that, we can actually start with an alkane and we can halogenate it. All right? So, how could we convert this methyl cyclohexane to this bromohydrin over there? Water and strong acid. So water and strong acid are conditions for a hydration type of reaction, right? And what would that be reacting with? So let's think, should we work forward or backwards here? We can work both ways. Okay, well, let's work forward first. What kind of reaction do you think we're going to use here? A what? A radical reaction, right. We're not going to use a combustion reaction? No, it's going to be hard to get back to that product from CO2. Okay, so which reaction did we say was best for synthesis? Bromination, right? So let's do a bromination reaction. So we're going to use Br2 and H nu. All right, where's the bromine going to go? To the tertiary position, right? Just like we did on the last slide. All right, now let's think retrosynthetically from the product. Okay, how do we generate a halohydrin like this? Yeah?
Could the bromine go to more than one location, though?
The bromine could go to more than one position, but we just saw that bromine is very selective for the most highly substituted position. Right? If we tried to chlorinate it, we'd get some chlorine here, but we'd get some here, we'd get some here, and we'd get some here, maybe even some in the methyl group, and we'd get a big mixture of those positions. By doing the bromine, it's going to be very selective for that tertiary position. Okay? All right, so what can we make that halohydrin from? An alkene. All right? Like this. Okay? So what reaction is that? How would we do this? What do we do, Jake? Well, the hydroboration oxidation just is a hydration reaction. It adds an H and an OH, but it's anti-Markovnikov, right? So if we did that, the H would go where the OH would go where the bromine is. Yeah. Possibly, that would be one possibility. Let's think it out. So let's say we epoxidize this first. All right, so I'm just going to put, I guess we don't have a lot of time here, but put the epoxide like this, right? So then what would we do to open up the epoxide? Well, if we do water, then we get a diol. We could use acid, aqueous acid. Well, that's the same as water. What kind of acid? We need a bromine, right? We could add HBr to this to try to open it up. Protonates the oxygen, makes a good leaving group. Which side does the bromine go to? Goes to the more substituted side. Okay, under acidic conditions, always goes to the more substituted side. So we get a related compound, but we have those groups on the wrong positions. Yeah?
Elemental bromine, hydrogen peroxide, and then the OH negative.
So bromine, hydrogen peroxide, and OH negative, no, that sounds like you're a little bit mixing up the hydroboration. So all we really have to do here is use bromine, right? So if we add bromine to an alkene, it makes a bromonium ion. And then if we do the reaction in water, then in the second step, the water is the nucleophile to open up the bromonium ion. Right? Just like the reaction on the right, the nucleophile comes in on the more substituted side, but that puts the OH on the more substituted side. So it just reverses the order. Okay? So then what about this step? Let's just finish here. We just need a strong base to do an E2 elimination. So we could just use something like methoxide or something like that. Just as this would just be E2. Okay? All right, so don't forget about the review session tonight at 6:30, right? And I will see you guys tomorrow.